Yeah, ladies and gentlemen, I'm glad to be able to present the next video tutorial on concentrating solar power for desalination. First, to my person, I have a diploma in mechanical engineering from the University of Clausthal and a doctoral degree from the University of Oldenburg in Germany. I've been working over 17 years on renewable energy sources and concentrating solar power at the DLR Institute of Technical Thermodynamics in Stuttgart. Concentrating solar power for desalination is an element for a sustainable future supply of water. I will talk about the technical implications of this concept, about the demand-side assessment in the Middle East, North Africa region. I will present a sustainable supply scenario for water in the MENA region, and I will talk about the environmental impacts related to this scenario. First technology option we have is reverse osmosis. It's desalination with membrane technology. What you see here are the typical pressure stacks for reverse osmosis plant and the pressure pumps in such an installation. A reverse osmosis plant consists of a seawater, raw water pretreatment plant, which protects the rest of the equipment from aggressive agents that may be contained in the seawater. The high pressure pump, which presses the water into the membrane stack, where the desalinated water goes through and is at the end post-treated, cleaned and used as fresh water. The brine with the high salinity is discharged to the seawater, and part of the energy used for the elevation of the pressure can be regained in an energy recovery unit, which would be here. The typical power demand of a reverse osmosis unit is between 4 to 6 kilowatt hours of electricity per cubic meter of desalinated water. It depends on the salinity of the seawater. Starting with 25 kilograms per cubic meter of salt for brackish water and diluted seawater, there would be a need for 4 kilowatt hour per cubic meter, while in very high salinity waters with 50 kilogram salt per cubic meter and more, the electricity demand would be about 6 kilowatt hours per cubic meter for modern RO with energy recovery. Next technology is the multi-stage flash desalination system. This is a distillation unit, so the water is distilled and condensed in order to get rid of the salt, and very large units are already working all over the world, mainly in the Persian Gulf, like you can see here. The concept is that there is steam from a power plant, usually heating seawater coming in from the sea. The seawater is preheated, heated and to a high temperature. And in the first stage of the multi-stage flash vent, the pressure is reduced so that the brine starts to boil. A vapor is produced, which is later condensated here and gained as distillate from all the stages for fresh water. Always when the brine changes to another stage, the pressure is reduced further. And so always at a lower temperature, water starts to boil, starts to flash. That's why the name multi-stage flash is used. And vapor is produced, which is condensed by the incoming cool seawater, which is preheated on the other side. So this is a very simple concept, very robust technology. Stages can be between 20 to 40, so always the heat of evaporation is used again. There is a demand of low temperature heat between 70 and 125 kilowatt hours per cubic meter, and the steam used for that has a temperature between 100 and 120 degrees centigrades. The electricity used for this is between 3 and 5 kilowatt hours per cubic meter, so it is not much lower than the electricity demand of reverse osmosis, and in addition to that it requires heat. But it is a very robust desalination system. The third system is multi-effect desalination. You can see here some plants. They're a little bit smaller than the multi-stage flash usually, but also it's proven technology and applied worldwide in many cases. The concept is slightly different. You have the saline feedwater here coming in, and it is sprayed over a heat exchanger. Inside the heat exchanger, you have steam from the power plant at low temperatures, and this energy is transferred to the water sprayed on the heat exchanger and thus some vapor is created in the stage. The vapor is going out of the stage, while the brine with a higher salinity is discharged to the sea. The vapor from the first stage now is used in the same heat exchanger in the second stage for heating, and again seawater is sprayed on this heat exchanger, partially evaporated and going to the next stage. In this way, the heat of evaporation from one stage to another is recycled, one could say. This principle can be repeated for about 8 to 12 stages. The heat required is similar to that of multi-stage flash. It's between 70 and 125 kilowatt hours per cubic meter, but it can have a lower temperature. That means the steam can have a lower quality than for multi-stage flash, a temperature between 55 and 75 degrees centigrades. And the electricity required is much lower. It's between 1 and 2 kilowatt hours per cubic meter of water. So these are the three systems that are possible for seawater desalination at a large scale. And of course, they can now be combined with concentrating solar power plants in different ways. The concentrating solar power plant is composed by a conventional steam cycle power plant, like here. The steam cycle is usually fired with fossil fuel to produce steam, like all the plants that are used at the moment in Saudi Arabia or in South Africa with coal, or in Australia, also using coal. So this would be a conventional system producing electricity. Electricity is fed to the grid, and a part of this electricity can be used for reverse osmosis, pumping energy, producing water for desalination. Now the CSP plant has some additional features. It has a large concentrating solar field, which can produce heat during the day. And always when there is solar heat from the sunshine, no fuel is needed to power the plant. And if there's a second solar field installed for nighttime operation, this excess energy can be stored. And then at night it can be withdrawn from the storage and still used for power generation in the power plant. So with the concentrating solar power system, it is possible to operate a power plant day and night if solar field and storage is large enough, and if the site is good enough to produce a very continuous solar energy during the whole year. Another option is to use a combined heat and power system using the reject heat from the power plant, which usually goes into a cooling tower, for the multi-effect and the multi-stage flash desalination systems. Again, this would be a conventional system already used many times in the Arabian countries, just putting fuel into the power plants and using combined heat and power for desalination and electricity generation. And the new thing would be only to add a solar field and reduce the consumption of fuel to produce the same amount of power over the year. There's a different impact of cooling systems on the power plant efficiency. For example, if there is a wet cooling tower with water evaporation, like in most of the steam cycle power plants worldwide, we would have at very low operating temperatures of the cooling tower, we would have the highest possible efficiency of about 100%. And this efficiency goes down when the temperature of cooling increases. So temperature of cooling increases, the condensing temperature, so the efficiency goes down of the power block, and electricity is lost, one could say. So wet cooling towers would have this efficiency range, while dry cooling towers, drying the solar power plant, cooling the solar power plant with air, would have a relatively lower efficiency range. And if we cool the solar power plant with a multi-effect desalination system, it would have more or less the same efficiency as a system with a dry cooling tower. If we would use a multi-stage flash system for cooling the power plant with a higher temperature range, the efficiency would be still lower, and we would lose about 25% of the electricity produced in the power block. So this is the impact of different cooling systems on the power plant efficiency, which is considerable. Another very important aspect is the coverage of load during the whole year and over the time. For example, if we have a task to cover, let's say, about 10 megawatt capacity with a constant load with renewable energy, we have three options. We could install a concentrating solar power plant in hybrid mode. That means it can operate with solar energy or with fossil fuel. And we will also install a thermal energy storage as described before. With such a plant, we need only to install the 10 megawatt CSP plant, And over the year, we would have to add about 10% of the energy into the same plant, but with natural gas, with fuel. What you see here is the 10 megawatt constant load covered most of the time with solar energy. And when the storage is empty and there is no sunshine at that moment, we would have the same power block running on fossil fuel for a short period of time. And then again, solar energy is available and the plant goes on operating always with the same capacity, sometimes with fuel and sometimes based on solar energy. This is, of course, an advantage because the efficiency of the plant will always be at a maximum level because it always operates at a nominal production point. An alternative to provide renewable energy for a 10 megawatt load would be photovoltaic systems. The disadvantage of photovoltaic systems is that over the year, the capacity increases, goes to a maximum, and then for the nighttime, it goes down to zero. The next day, it starts again. It means even in a very good site like the one used here, we have an interrupted operation of the PV system, and the gaps which are left have to be filled with electricity from another source. That means from another backup plant that may be on the grid. This means we will have to install 10 megawatt PV capacity plus 10 megawatt backup capacity, and to fill the gaps, we will have to add 75% of the energy from natural gas or other fossil fuel sources in the backup plant. Now, if we look at the wind park supplying 10 megawatts, we would have a similar picture, but not necessarily interrupted every night, but also very fluctuating, partially unpredictable fluctuations here, some bigger, some smaller, which will provide energy over the year, but the gap, again, will have to be filled by a backup plant with the same capacity. In this case, under this site conditions, we would have to install 10 megawatt wind park, 10 megawatt backup plant, and we would have to add 60% of the energy by natural gas over the year. As a consequence of this, we can say that a complementation of renewable energy by the grid, which is possible, is only feasible if the renewable energy capacity is small compared to the grid capacity. If the capacity of the renewable energy is large as the maximum capacity required by the grid, we will have flexibility problems here because it is not easy to operate a conventional plant in such a mode. It is shut down completely and then shut on again in a few hours. So this would be a very difficult situation, which usually must be avoided by utility operators. The next step of the analysis was the assessment of the water demand in the future of the MENA region. For this, we have analyzed the population prospects. It can be expected that the population doubles until the year 2050. Economy will grow to a level comparable to the national economies of Europe. And of course, the efficiency of the water sector will increase. And all these factors lead to a growth of the water demand in the region from about 270 billion cubic meters per year to over 450 billion cubic meters per year. The main sector of demand will be the agricultural sector. Irrigation is, of course, a need for water in the MENA region, which is very important. Afterwards, there's the demand for municipal water, and only a small portion goes to industrial demand. However, in the future, with a growing economy, the importance of the industrial and municipal demand of water will increase, while the agricultural water demand will be stagnating. If we compare the water demand overall over the region, which is composed of 20 individual countries, which are added here, and compare it to the sustainable water which is available and can be used in the future, we see that here there is already a gap between the demand and the sustainable water available. And this gap, unfortunately, is growing significantly in the future. The conclusions of the water demand assessment in the MENA region are the following. The MENA population will double by 2050 from 300 million people today to 600 million people in the year 2050. The MENA economies will approximate European level by the year 2050. The MENA water sector will achieve a reasonable efficiency by 2050 if related measures are taken by the governments. The water demand under this scenario would grow from 270 billion cubic meters per year in the year 2000 to over 460 billion cubic meters per year in 2050. The deficit accordingly would increase from 50 billion cubic meters per year in 2000 to 150 billion cubic meters per year. This is 2 times the volume of the Nile River. So this is really a challenging and very critical situation in the region. Even extreme efficiency measures could limit the deficit only to 100 billion cubic meters. So it would be reduced a little bit, but it cannot be eliminated completely. That means as a consequence that the efficiency and new sources of water will be required to cover the growing water deficits in the MENA region. And of course, one of those new sources is seawater desalination. When we have developed the water supply scenario, we have applied the following methodology. First, we have assessed the water demand from the year 2000 to 2050 as described before. Then, we have assessed the total and also the coastal CSP potential for seawater desalination in order to see how much water could be desalinated by concentrating solar power in the different countries. Then we have assessed the opportunity for the replacement of old desalination plants, which will of course open a window for the installation of new plants. The top priority was set for efficiency gains. That is the first measure and the most cost-effective measure that can be taken for increasing the supply of water. The second priority was given to the reuse of wastewater, from municipal water to use it for irrigation, for example. The third priority was set for the sustainable use of surface and groundwater extractions, which are of course available, but unfortunately very limited in the MENA region. The next priority was set for existing and for planned conventional desalination plants, which are already in the pipeline of being constructed in the next 5 to 10 years. And the last priority was given to CSP desalination plants after the year 2015. That means deficits that would occur after 2015 would preferably covered with CSP desalination if no other options are available and the scale needed. To unsustainable water extractions, to the overuse of groundwater, no priority was given because this is already a problem rising in many regions. For example, the groundwater level of the city of Sana'a in Yemen is falling by 6 meters per year due to an overuse of groundwater. There is a lot of groundwater in the Sahara region, but unfortunately this is fossil water, it is not renewable. And when one takes it out, the groundwater level falls quickly and the water is in danger of being polluted or even extinguished. So this is the result for the 20 MENA countries. We have a significant but more or less constant and already used amount of natural water, renewable water that is used in the region. This is groundwater and surface water that is renewable every year. Already today there is a big overuse of water, which is the yellow area, and this overuse of groundwater still will increase in spite of measures for efficiency and in spite of using fossil fuel desalination systems and wastewater reuse increasingly in the region. And also efficiency measures can be applied and will provide a significant share of future water sources. However, as I said before, the gap would increase. And it would take about 20 years until this gap can be substituted by the use of solar energy for seawater desalination. This would be this area here. So the problem is that the technology is there, okay, but there is zero production of solar desalination today. And to reach a production of about 50 billion cubic meters per year needed here, for example, will easily take 20 or maybe 30 years of time. It is not possible to achieve that goal faster. So this is a scenario which is optimistic because it shows, okay, the problem can be solved. There is enough energy to desalinate the amount of water required. But of course, it will take a long time. It will take 2 to 3 decades to achieve that goal. And it is not sure if the groundwater resources will last long enough and be available still in the year 2025. So it is due time to start with that development. Conclusions of the scenario analysis. Sustainable supply must be initiated immediately in order to avoid groundwater collapse in the medium-term future. The increase of efficiency of water production, distribution, end use and management is one of the top priorities of such a strategy. Also, the increased reuse of wastewater. The introduction and dissemination of CSP desalination plants should start immediately, because it will take a long time until the CSP industry will be big enough to cope with the problem. The overuse of groundwater will still increase to 70 billion cubic meters per year in the year 2020. This is the volume of the Nile River. It is a huge amount of water that will be taken from groundwater, which will not be renewable. So the danger of really going into a critical situation is really large. Conventional desalination will also grow by a factor of 5, which will require the consumption of a lot of fossil fuels for seawater desalination. This means all measures that are mentioned here should be taken parallel to avoid groundwater collapse, which is the first priority of such a strategy. Environmental impacts of conventional seawater desalination are considerable. For example, we have seawater intake for desalination and for the cooling system, which may cause impingement and entrainment of organisms when on the water intake. We will have airborne emissions of pollutants and carbon dioxide that are caused by the generation of electricity and heat required to power the desalination plants, and this amount of energy is considerable. We will have to add chemical additives and biocides in order to avoid the fouling, foaming, corrosion and scaling of the desalination plants. And these chemical additives may finally appear in the brine and be rejected to the seawater. The hot brine discharged to the sea, also with a high salt content, will cause danger for local species, which will not be able to support high gradients of salt or temperature in the water. So these are the problems of conventional seawater desalination. And if you imagine that in the future about 70 billion cubic meters per year should be desalinated, so the environmental impacts would not be acceptable going for conventional seawater desalination. This is the picture. We have a typical intake, we have screening, filtration, then we have the additives. In order to protect the desalination plant, we will have to add a lot of heat and power, which will be taken from fossil fuel to power the plant. And at the end, we will have a discharge to the sea. So there is an alternative, which is the concentrating solar power desalination plant developed at the moment. We have an intake from horizontal drain under the seabed. So the filtering is through the seabed. And of course, no organisms can be sucked into the tube by this system because the water is sipping through the stone and through the sand. Then we add nanofiltration and ultrafiltration here, and thus avoiding a lot of chemicals that would be needed if we would leave those agents inside the seawater. The energy is only to a small extent from fuel, but to the largest extent from concentrating solar power with storage. So the emissions to the atmosphere would be reduced considerably by providing solar energy to the desalination plant. And finally, the discharge is through multiport diffuser, which allows for a fast and quick dilution of the brine in the seawater. So this is a plant that would be acceptable in terms of environmental impact. It would have very low environmental impacts, but all these components, this one, and that one, require more energy than the conventional desalination plant. And providing more energy by fossil fuels, of course, again would lead into a problem. But providing more energy to the desalination plant by solar energy may lead to a future sustainable supply. Conclusions. Large-scale conventional seawater desalination would create significant environmental impacts, but CSP can reduce energy-related emissions to a few percent compared to the conventional systems. Beach well horizontal drain intake and nanofiltration can reduce the chemical additives. Horizontal drain intake can reduce impingement and entrainment of organisms. And a multi-diffuser discharge can avoid high concentration of heat and salt in the water after discharge. So the advanced CSP seawater desalination can be compatible with the environment, even if it is applied at a very large scale. Why use CSP for seawater desalination in the MENA region? There are 5 very good reasons for that. The CSP potential is very large, even at the coastal sites. There is a good seasonal correlation of solar energy availability and the water demand. Solar energy is most abundant in regions with highest water scarcity. In fact, solar energy is the cause of water scarcity, and if we use it to solve the problem, that is a very elegant approach. CSP can provide renewable baseload power for uninterrupted operation of desalination plants. This is very important to have a good return on investment and to have a long life of the power plants, which would not like to go to part load all the time. Solar power treatment of raw water and brine can avoid chemical additives and, of course, increase a lot the compatibility of the plants with the environment. Here you can find some information on the websites about the studies on solar seawater desalination. Many thanks to the Federal Foreign Office for funding the Enamina project and to the colleagues of the Institute of Technical Thermodynamics and the Institute of Solar Research that have been helping to make this presentation. And thank you very much for your attention.